Einstein was right. The discovery that brings us closer to unraveling the mystery of antimatter. Engineers at CERN introduced liquid helium into the system in order to maintain antimatter at a temperature close to absolute zero, which is the lowest possible, around -270 degrees Celsius. Researchers have achieved a fundamental breakthrough in understanding antimatter, a mysterious entity that was widely present in the early universe. Antimatter represents a counterpart to matter, which forms the basis of stars and planets. In the genesis of the universe through the Big Bang, both substances emerged in identical amounts. The most recent study has revealed that they both react to gravity in the same way. Over decades, scientists have devoted their efforts to unravel the distinctions and similarities between both substances in order to shed light on the birth of the universe. The revelation that antimatter reacts by rising instead of falling in response to gravity would have completely challenged our understanding in the field of physics. Now, it has been confirmed for the first time that antimatter atoms experience the force of gravity, opening up new opportunities for further research and theories. Do they fall at the same speed? For instance, during the Big Bang, it is assumed that matter and antimatter mixed and annihilated each other, leaving only light. The reason behind this phenomenon is one of the great mysteries of physics, and discovering the disparities between the two is the key to solving it. In some way, in the early moments of creation, matter prevailed over antimatter. The answer to how it reacts to gravity could hold the key, as explained by Dr. Danielle Hodgkinson, who is part of the research team at CERN, the European Organization for Nuclear Research in Switzerland, one of the leading centers for particle physics studies. We don't understand how our universe ended up being dominated by matter, and this is what drives our experiments, she shared with me. Most of antimatter has an ephemeral existence in the universe. Therefore, to conduct experiments, the CERN team had to generate it in a stable and enduring manner. At CERN, a facility was constructed that incorporates an extensive ring formed by magnetic fields in order to have control over antimatter. Professor Jeffrey Hangst has dedicated 3 decades to creating a specialized facility that enables the meticulous construction of thousands of antimatter atoms from subatomic particles, as well as capturing and subsequently releasing them. Antimatter emerges as the most captivating, enigmatic, and intriguing substance you can conceive, he states. According to our current understanding, it is conceivable to envision the creation of a universe identical to ours, with individuals like you and me composed exclusively of antimatter, Professor Hangst explained to me. Exploring this possibility is genuinely inspiring. It represents one of the fundamental unanswered questions about the nature and behavior of this substance, he added. Let's begin by defining what antimatter is. First, it's important to understand what matter is. Everything we encounter in our environment is composed of it, including the tiniest particles known as atoms. The most basic atom is hydrogen, which makes up the primary element in the composition of the Sun. A hydrogen atom consists of a positively charged proton in its nucleus and a negatively charged electron orbiting around this nucleus. In the case of antimatter, the electrical polarities are reversed. Let's consider antihydrogen, which is the antimatter counterpart of hydrogen used in CERN's research. In this case, there is an antiproton with a negative charge in the nucleus and a positron with a positive charge orbiting around it. Antiprotons are generated through particle collisions in CERN's accelerators and transported to the antimatter laboratory at speeds close to the speed of light, making them uncontrollable for researchers in that state. The first step is to slow them down, which is achieved by passing them through a large magnetic ring that gradually reduces their energy, making handling easier. Subsequently, both antiprotons and positrons are directed into a large magnet, where they combine to form thousands of antihydrogen atoms. This magnet creates a magnetic field that holds the antihydrogen, as any contact with the container walls would result in its instant annihilation, as antimatter cannot survive contact with our world. By deactivating the magnetic field, the antihydrogen atoms are released, and sensors record whether their direction of fall is upwards or downwards. Some theoretical scientists have suggested the possibility that antimatter might experience an upward fall, although the majority, including Albert Einstein in his general theory of relativity formulated over 100 years ago, postulates that it should behave the same way as matter and fall downward. Scientists at CERN have achieved confirmation with an unprecedented level of certainty that Einstein was right. However, it's important to note that the fact that antimatter doesn't fall upwards doesn't necessarily imply that it falls downwards at the same speed as matter. The research team plans to refine their experiment in the next steps with the goal of increasing its sensitivity and detecting possible subtle differences in the fall speed of antimatter. If any variation is found, this could shed light on one of the fundamental mysteries, the origin of the universe. The results of this research were published in the specialized scientific journal Nature.